All right, today, so I ran out of water jokes. I literally ran out. And when you Google water jokes, I've seen them all. I've already Googled enough. Anybody got a water joke? The only thing left, oh no, wait. I do remember one. Let's try this. Wastewater joke, far side. Let's see if I can find that. Oh no. There's a Far Side comic that's a cool wastewater thing. Oh. Alright. I'll have to look that up for you later. Anybody got a joke they can tell us? Alright, last ditch effort then. Wastewater joke. Let's see. Bacteria jokes by Norwico. What do you call an amoeba that crosses the road, jumps in a mud puddle, and crosses the road again? A dirty double crosser. Actually, I've seen this page before. Most of them are really lame. So, sorry about that. Yeah. Okay. Let's get on to the material today then. We've got, we started this last time, talked about disinfection. We saw our Star Wars ray gun, our UV chamber, and then I realized that we actually do have a few more slides than I remembered on UV, so we'll talk about that a little later. We talked about the history of disinfection and Jon Snow, and I guess you guys have been exposed to that. I think we ended on this slide. And the key thing to think about here, would you mind hitting the lights there, Jason? Is to realize that we've got different types of animals or microorganisms that cause problems and that are pathogens for humans. That's what we really care about, the pathogens. So bacterial pathogens, E. coli, cholera is also a bacterial species. We have other viruses that we worry about. And here's a rotavirus, for example. Cryptosporidium and Giardia are shown here. Let's see, adenovirus was there. And then we have amoebic cysts, okay? Ooh, so Entamoeba histolytica. And I'm not a biologist, so I don't get into the details of these. But the key thing we need to realize, maybe I need to update this slide actually, to put scale bars on here. Which of these are the largest creatures that we worry about on here?
Giardia?
Yeah, your Giardia is going to be pretty big, and your Cryptosporidium is going to be pretty big. Does this have a scale bar at all? No. I need to put scale bars on here. But your crypto, you can see this under a regular visible light microscope actually. If you had a sample of crypto, you could visualize it, see it with your naked eye. Bacteria, you can also see. Oh, so the size here, we're talking something on the order of 50 microns in size. Bacteria, instead of being 50 microns, they're down around 2 microns in size. So it's interesting. Crypto, we should be able to remove that pretty easily with filtration methods, and especially with membranes, we're going to remove crypto. Most bacteria we're going to be able to remove with membranes too, because membranes are like 0.1 micron microfiltration membranes. Bacteria are 2, 3, 4 microns in size, so you can usually remove bacteria. Viruses, though, are much smaller. A virus, you can't really see that with a regular visible light microscope. You got to use a scanning electron microscope or a transmission electron microscope. And like this rotavirus here, that's not a regular visible light image because light just is too large a wavelength to be able to see these things. We're talking like half a micron or even smaller in the nanometer size range. When we talk about nanoparticles, you may have heard in the news or in research symposia and things, we talk about nanoparticles. Viruses are on the same order of size as nanoparticles. 100 nanometers, 50 nanometers, 10 nanometer range. So it's a very different world depending on what we're talking about. The goals of disinfection, are framed here in terms of the regulations. So the ultimate goal of disinfection, of course, is to keep us safe, keep us healthy. But what that means for an engineer is you got to meet the regulations. So the regulations are written to try to keep us healthy, and then an engineer does everything around the regulations. I was just at a water conference in New Orleans. It's called WQTC, the Water Quality Technology Conference. And most of the research that's there, that's driven there, and the people that run municipalities and operate treatment plants, they care about meeting the regulations. And the EPA people were there too, talking about what should the regulations be. And the ones that we go by so far, the surface water treatment rule is a big thing that protects against Giardia, viruses, Legionella. We have this other stage 1 DDBP rule, setting maximum contaminant levels for trihalomethanes, haloacetic acid, bromate chloride. We'll talk about what disinfection byproducts are in a little more detail. You have this enhanced surface water treatment rule focusing on cryptosporidium. And a lot of these rules and new regulations came out after the Milwaukee incident with the crypto outbreak that we talked about last time. We've got these other rules, and the big one that isn't listed here, these are some of the more detailed rules and legislation that have been implemented. But the Safe Drinking Water Act is the big thing that we're doing. It sets maximum contaminant levels for lots of chemicals, but also for all these different microorganisms that we talked about. Okay, so here's a slide. This is the answer to the question that I want to pose to you all. What if we're going to add some disinfectant, some chemical to the water? What are the properties that it needs to have? Let's think about and discuss. Like, if you're gonna disinfect your water with some chemical, what are the properties? So we have a guest today. What's your name?
Caroline.
Caroline? All right, so Caroline, you haven't been in this class yet, but someone's going to tell you that we're going to put chemicals in your water to kill the bugs. What kind of chemicals do you want or not want in the water?
I want ones that are safe for me to ingest.
Okay, that's a big thing, right? So that it's got to be safe. Obviously, we're trying to prevent illness, right? So the chemical that we put in the water can't be poisonous to us. All right, so that's first big thing. You're off the hook now. Good job. Good job. First question answered. Katie, anything else?
I want to make sure that by the time it got to the furthest house, I was still cleaning the water.
Okay, it's gotta remain in there as long as you can go. What do we call that? Did you talk?
Residual?
All right, residual. So you guys already talked about disinfection in your other classes then, right? So it's like, yeah. All right, so you should have it figured out. What else? Tyler? What else would you care about for your disinfectant? So we said it's
effective.
okay, it's gotta be effective. It's gotta actually kill the bugs, right? All right? There's several other things, but one big one that I think, just on a practical level, the people actually doing this would care about. Cheap. So, Kyle? Yeah, it's gotta be cost effective, right? There's lots of ways to kill bugs, and many of them are way too expensive to actually use on a mass scale. So you guys covered this already. We've got to destroy the kinds and the numbers of pathogens in the water. It's got to do so within a practical time period. We talked about it being effective, right? And that's key, but it's got to be effective quickly also. That's what this is saying, the time. It's got to work at the right temperature of the water. So that's a caveat that, if you were doing research, you would want to make sure to cover the temperature ranges of interest. It's got to be effective at variable composition, pH, different conditions of the water. It's got to work on all different kinds of waters, not just one kind of water. Can't be toxic to humans, that's what Caroline told us. Oh, we don't want to kill our animals either, right? Our domestic pets. It's got to taste good, be palatable. It's got to be cheap. It's got to be safe and easy to store, transport, handle, and apply. And we have to be able to determine its concentration and provide the residual that Katie mentioned to us. All right, so you guys got that covered. We're going to cover a little bit for wastewater too. What about wastewater? What are the properties? Now, with wastewater, we actually do not want a residual. We don't want to send disinfectant out to the lake, so there's got to be a way to remove the disinfectant before it gets back to the lake or the river, whatever's receiving our effluent wastewater. We don't want to produce cancer-causing compounds. It's got to work, and we don't want it to be toxic to fish unless we can remove it. Far and away, the big one that we deal with is chlorine. Chlorine is the main disinfectant used in the United States and around the world. Okay? You can get it in chlorine gas, sodium hypochlorite liquid, or calcium hypochlorite solid. So we already dealt with the liquid form of chlorine in the lab that we did. Chlorine gas is shown here. Here are some huge cylinders of chlorine gas being used at this water treatment facility. And in the supplemental slides, it has a lot of other pictures of these chlorine gas cylinders and how they use them. And then calcium hypochlorite. So Kate, Kim, you guys were planning to use these little pool tablets, right, for disinfection for Nicaragua?
Mm-hmm. They're basically like little tablets of, it was the NaO.
Oh, it was actually sodium hypochlorite?
That's what I thought it was.
Okay.
I could be wrong.
A lot of the tablets are made of calcium hypochlorite, but maybe they do some combination. I'm sure there's lots of different proprietary kind of mixtures.
Mm-hmm.
But, okay, so I was thinking maybe it was the calcium hypochlorite.
And I could be wrong.
Or it could be both.
Read a lot of literature.
All right.
Yeah.
But that's a solid form, so that has certain advantages, like in that third world situation, or in your pool situation when you want to just throw a chlorine tablet in your pool. How do we actually get it into the water? So these are two gas mixers here. So you have a chlorine diffuser. The water's coming in, and then you have a chlorine diffuser and a little rapid mix chamber to get the chlorine mixed in there, and then you have a contact chamber to give it time. So one big thing with chlorine, with all disinfectants, you have to have the right dose, but you got to give it enough time, and so here's your contact chamber at the end. Here's another system for it, a jet nozzle. Again, it's just providing mixing this reactor tube to get it all into the water. So similar to our other chemicals that we've added. When we talk disinfection, we're talking chemistry. So you gotta pay attention to the chemistry here. Chlorine gas goes very quickly into the aqueous phase. We could have added another property to that previous slide. It's got to dissolve easily in water. And chlorine is great because it does dissolve easily in water. So the gas gets dissolved, and then very, very quickly again, the aqueous chlorine, the dissolved chlorine, reacts with water to form our hypochlorous acid, H plus and Cl minus. Okay? This is pH dependent, of course, so if you have a high pH, it's going to push it the other, high pH is going to be low H plus concentration, and it's going to be pushed in this direction. If you have a low pH, you're going to have a lot of hydrogen ions, it's going to push it in the other direction. It's a very fast reaction. Now notice, let's see, okay, HOCl then dissociates, so we have this HOCl molecule that also dissociates to give you another hydrogen and another hypochlorite ion. Here's an interesting and a key concept here. HOCl is about 80 to 100 times more effective against E. coli than the OCl minus. We call this the protonated form. The protonated form is the one that's got the proton on it, right? So HOCl is more effective than this OCl minus. So what does that tell you about the pH where you would have better effectiveness? You're going to have better effectiveness at high pH or low pH when you're dealing with chlorine? High pH? Why do you say that?
because of Le Chatelier's principle. If there's, or no, low pH.
Ah.
Sorry, I got it backwards. Like
Okay.
high concentration of H+ ions.
Good. Yeah, I just made that error, or made that mental mistake too when I was describing it a minute ago, so you're in good company, I guess. But yeah, the more, if you have more H+ ions in solution, then you have lower pH, that's gonna push it, actually I should be talking about this one, right? More H+, it's gonna push it in this direction, so you're gonna have more HOCl, and since HOCl is more effective, you're gonna get better kill. So that's a really good conceptual question for final exam. See if I can remember to include that in there, or some similar kind of question. Oh, notice this, free available chlorine is defined as HOCl plus OCl minus plus Cl2 aqueous. Again, most of the Cl2 aqueous actually just dissolves quickly, so we're mostly just talking about these two species when we talk about free chlorine. Free chlorine is what we measured in the lab. That little hot kit where we added the chemicals and it turned pink. When I say HACH, that's H-A-C-H, the company name for that little device that we used. Turns it pink, it's measuring these two things, the HOCl and the OCl minus. Here's a graph that just helps drive home the pH dependence point. The pKa is about 7.54 at 25 degrees C. Changes a little bit at a different temperature, but notice that if your pH is down below this isoelectric point, you're going to have mostly HOCl in solution, and if it's above about pH 8 or 7.5, you're going to have mostly OCl minus. All right, it's key to understand that, the concepts in that graph there. All right, let's do an example problem. We're going to ask ourselves, what's the pH of water at 25 degrees that contains 0.5 milligram per liter of hypochlorous acid? We're going to assume equilibrium has been achieved. We're going to neglect the dissociation of water. In other words, we're going to keep it to the simple equations, make an estimate here. May not be justified. Report the answer to 2 decimal places. Let's, before we do this, I just had another thought. In the lab, so we just told you that when you add chlorine to water, you get more H+ ions, and so Kim realizes now that means your pH goes down, right? What happened in the lab though, when we added our disinfectant? Do you remember, Meg? Were you doing pH or are you doing the other one?
I was. Well, our pH wasn't working. Remember, we had the really fluky.
Oh, okay. Yeah. Anyone remember what happened? Yeah, at the really high concentrations. It went up. Yeah. Our pHs, when we had, DI water was around 5.5 or 6, and when you added more and more sodium hypochlorite, the pH went up. Is that consistent with what we're talking about here? Well, let's see. We added the sodium hypochlorite, so we added NaOCl minus. The Na and the OCl will separate very quickly, so you get Na plus and OCl minus in solution. So that OCl minus then will react with whatever H+ ions are around to form HOCl. So the more of this you add, the more of this you're going to take out of the system, and that means your pH goes up. Does that make sense? When we add chlorine, on the other hand, we're adding the chlorine gas, and it goes first to HOCl. So in one situation, we're adding the HOCl. Well, for one thing, the H+ came off first, and then this HOCl gets added to solution, and it dissociates to give you even more H+. So this is another key concept and an even better exam question. Why does pH go up when you add sodium hypochlorite to water, but it goes down when you add chlorine gas to water? I'm really going to have to try to remember that one. That's great. Okay. If you understand that, then you're way ahead of the game. You're way ahead of the general population in terms of understanding acid-base chemistry.